Hi, good day everyone. This is Robotics and Automation course. The topic for today is about spatial descriptions transformation. In the diagram, it describes about the rigid body configuration. So there are two frames you can see in the diagram. So what is a frame? It refers to a coordinate in terms of Cartesian coordinate system. So here is the frame. This is one frame. We call this one the frame A. With the unit vectors, the XA, YA, and the ZA. These are, we call this one vector components. And the rigid body is defined or described as the frame B. So here is the frame B with the coordinates XB, YB, and ZB respectively. So this is in a certain point and in a certain position. So this is our origin of frame B and this is the origin of frame A. So between the 2 points, we have a projected vector, which is the position. So the position is describing the P to A. This is the point P, this one, is relative to the origin A. While the orientations are the XB2A, YB2A, and the ZB2A. This is to describe rotations of B with respect to A in the rotation matrix. So here is the rotation matrix. Here is the rigid body configuration. Here is the matrix of the rotation. And to determine the XB2A, we have take the rotation matrix and multiply that with the XB with respect to the frame B. And here it is. For the XB2A, it will be equal to R B2A, multiply that with the matrix 1, 0, 0. While the YB2A is again rotation, multiply that with a 0, 1, 0. For the ZB2A is multiply that with R rotation with the 0, 0, 1 matrix. And summarizing the rotation, our rotation from B to A is equal to the respective rotations of XB to A, YB to A, and ZB to A. So for the rotation matrix, each of the component, each of the rotation represents a dot product. So for the XB to A, we have here the take all the XB, multiply that with the XA, YA, and ZB respectively. That's the dot product to determine the XB to A. While the YB to A is the second column in the matrix. This is the first column, which is the XB to A. And the last column is the ZB to A. And looking the matrix in terms of horizontal, looking the rows in terms of rows, so that will be the transpose, which is XA with respect to B transpose. here, presenting to you the slides or the frames of frame A. So this is our frame A. Okay. And placing the same frame with the same origin of the frame A. So this is the frame B, XB, YB, and the ZB. So this is the frame B. And the frame B is known as the body attached frame. So this is a correction. This is correction. So this is correction. This is, by the way, let me erase this one. How to erase for a while. Let me erase this one. So to correct this one, this is for a while. So this is actually our frame B, and this is our frame A. To correct that one. The rotation matrix of this will be R, B, to A is, since they are placed in the normal position, in this case, this is at no rotation. What will be the matrix at no rotation? So, writing down that one, you have here the, for the A, for the XB to A, you have here 1, 0. This is 1, 0, 0. For the YB to A, this is 0, 1, 0. For the ZB to A, this is 0, 0, 1. If the diagonals are in unity, this denotes as the rotation at this denotes at no rotation happens. Okay. Okay. And the next slide. We have the same frame. Okay. Frame A. And the frame B. So that's the frame B. So this is our frame B. And this is our frame A. In this diagram, to determine the, to prove that our R, I mean X B to A is equal to, our X B to A is equal to the dot product of this is XB, XB. So this is the XB, XB. Multiply that or that product with the XA, the reference YA, and the ZA. This is ZA. Okay. So in this analysis, the dot product of XA dot XB dot XA is equal to This is the direction of XB and this is the direction of XA. So XA dot XB is equal to, since these are unit vectors, magnitude of 1, cosine of the angle theta, the definition of the dot product. So what is the theta? The theta here is equal to 0 degrees. So our XA dot XB is equal to cosine 0 is 1. So therefore, this is 1. How about the XB.YA? So you look at the XB and this is the YA. It's 90 degrees. Cosine 90 is 0. This one is equal to 0. How about the XB.ZA? So here is the XB again. And this is the ZA, 90 degrees. So cosine 90, 0. Okay, so this is for the dot product of the XB to A. Next, the same, this time for the Y, the YB. So determining the YB, so you have here the YB to A, rotation of that will be the dot product of YB dot XA and YB dot YA and YB again dot ZA is equal to, so what is YB dot XA? So here is the YB. Where is the XA? Here. So it's 90 degrees. So this is 0. And what is YB dot YA? So this is YB and YA is it's 0 degrees. So cosine 0, it will be 1. That's it. Then YB dot ZA. So this is the YB. And where is the ZA here? This is 90 degrees again. So you have the value here, 0. So therefore, this is for the rotation of YB to A. So this is 0, 1, 0. Okay. Next. So this is again correction. This is B. And this is A. The same frame again. But this time, we determine the rotation that is at ZB. So ZB to A is equal to, bring the dot product. So ZB dot XA, ZB dot YA, and ZB dot ZA. So what will be this one equal to? So look at the vectors. Your ZB dot XA. So here is the ZB and XA, 90 degrees. So since this is 90, the value here will be 0. The dot product of that will be 0. And next is ZB dot YA. So here is the ZB and here is the YA, again 90 degrees. So this is 0. And ZB dot ZA. So this is ZB, this is ZB, this is ZA. 0 degrees. So the value of this is 1. So take note that how we obtain these values, the definition of the dot product, for example, A dot B is defined as magnitude of A, magnitude of B, cosine of the angle thetas. For unit vectors, like magnitude of A, the value is equal to 1. That's why you notice that this is the value of this is all 1. Next. So this is T. Again, this is B. And this is A. Here, continue. Now, this is the case that the frame B is rotated with respect to frame A, and considering the point P in question, which is with respect to frame B, what will be the uh, relationship? What will be the equation for this formulated? So our frame A, this is frame B, and this is frame A. So to determine the rotation, now this is at a certain rotation. We have here at a certain rotation, we determine the rotation of, we want to know the P to A at a certain rotation, and with given position P, or defining the position P, so which is relative to A with respect to frame A. So therefore, we're looking for the P to A. So bringing the matrix for that. So you have to get the X. To determine the P to A, so you bring the coordinates of Y, X, Y, and Z. So that will be our X A with respect to B. This is our Y A with respect to B, and Z A with respect to B. That product of that with the P with respect to B and P to B, and this one P to B. So in order to determine the final position P to A, the matrix will be XA to B, that P to B, YA to B, that P to B, and ZA to B, that P to B. This is equal to the rotation P to A P to B. So therefore, this one equals the rotation. Multiply that with P to B. Therefore, our P to A has the equation R B to A, multiply that with P to B. While so this is our for a while. Okay. So this is P. So this is the how to determine the final position of a certain point which is with respect to B with respect to B. So this is the final position. Again, the point P in question is relative to B. Multiply that with the rotation, you will get the final position with respect to the frame A. So this is the formula for that. Okay, so here is an example here. As you can see, the rotation is about, what are the given, by the way? The given here is this is the frame A, and the frame B is rotated about the x-axis. So how many degrees? Your YB originally was here, and your ZB is originally here. So as you can see, it is rotated by 90 degrees. So you will notice that the matrix of that will be 1, 0, 0 for the XB to A. This is 0, 0, 1 for the YB to A. 0, minus 1, 0 for the ZB to A. And looking at it horizontally, it's the respective transpose. So this is an example of rotating the frame B with respect to, when you rotate the frame B with respect to the axis of the x-axis. So here is the matrix of that. Next slide. Description of a frame. So again, here is the frame A. We have the frame B, the body attached frame. Between the 2 points, we have the PBORG to A. What does it mean, this one? It is the vector from the origin of B, frame B, relative to A. So this is the vector of that. So for the frame B, the orientations are XB to A, YB to A, ZB to A, and the position PBORG to A. So in frame B, you have the orientation and the position. Okay. Here this time, we have here the frame B is rotated about x-axis. So this is B again. This is A. So the result will be your YB is here, your ZB is here. And here is the position, the point P in question. Here is the vector of the point P in question, this one. So here it is. As I discussed earlier, that to determine the final position, you need the R and multiply that with the P to B. How about if the frame B is the origin of frame B is moved from the origin of A. So you will have a translation. Translation is this one. Again, this is B, this is A. So as you can see, we move the frame B, we translated the frame B at a certain point. So here it is the result of the translation. So here is the frame B. Here is the point P in question. This is the point vector, and here is the vector. And here is the the origin of frame A. This is our frame A. We rotated that about the x-axis. And where is the P2A? The P2A is the dash yellow arrow line. So this is the P2A. This is the vector which is with respect to the frame A. Now this is about translation. We establish a triangle between the two frames. So here is the vector, which is, we call that one PBORG to A. And the vector with respect to frame B is P to B. And this is the point P in question, which is, we are going to determine the final position, which is the P to A, this one. Okay, so your origin, from origin to P, this one, is is the same as, is the same point, which is from the origin of A, this is origin of A to P, is the same point from the origin B to point P, this one. Okay, and for the PBORG is the vector towards the origin B or towards the origin A. So that's the PBORG. So look at carefully. The origin B to P is the same vector towards the origin A, the position. Okay. So basing from the triangle, we can be able to determine the final position. The final position is equal to the PBORG to the P to B. This is the P to B, this one. Since this P to B undergone rotation, we summarize the transformation. So this is our general transformation. In order to determine the P to A, that is equal to P to B, multiply that with the R, B to A, plus PBORG to A. So we will be able to get the final position by using this formula. And using the 4x4 homogeneous matrix, we can be able to use the other way, the other method, which is P to A is equal to the T from B to A, multiply that with P to B. So the T is 4x4 matrix. This is 4x1, and this P to A is 4x1. So this is the 4x1, this is the 4x4, and this is the 4x1. In summary, we will have here the 3x3 homogeneous transformation. The final position can be obtained by P to A is equal to PBORG to A. This is to translate. And for rotation, that is RB to A times P to B. So this is our 3x3 homogeneous transformation. How about for the 4x4? This is our 4x4 homogeneous transformation. The final position can be obtained by the T, B to A, multiplied that with P to B. So both occurs here in the homogeneous transformation T, they translate and rotate. This is the example for the determining the final position. The question is, what will be the final position with the given position and the orientation of the frame B? So I will solve this one in the next video. That's all, and thank you.